Hello, welcome to our webinar on Crypto-Agile design to future-proof your embedded systems. If you have any questions, please use the Q&A box on your screen and we'll answer them at the end of the presentation. Now let's get started. Today we're going to talk about quantum computing and Y2Q, and then introduce Dilithium, a new quantum-resistant or so-called post-quantum crypto algorithm, one of a number of such algorithms being developed to augment and in some cases replace the public key crypto systems in wide use today. This is a webinar on Crypto-Agile design, so we're going to explain why you should tackle this problem now and how straightforward it is to adopt these new algorithms. We'll give you a quick demonstration of developer-friendly, production-ready tools. Let's start by introducing ourselves. I'm Jim Alfred, Vice President of BlackBerry Certicom. I worked in the embedded industry for over 35 years and witnessed a continuous stream of technology innovation. I've seen mainstream embedded design go from applications running on 8 and 16-bit micros to new multi-gigabyte applications hosted on 64-bit multi-core processors. When I joined Certicom in 2004, the use of public key cryptography, or even a concern for cybersecurity and embedded systems design, was fairly limited. Today, cybersecurity concerns and the use of public key cryptography and PKI are nearing ubiquity. Having seen the phenomenal progress in chip and computer design over my career, I'm keeping a close eye on the progress in quantum computing. I look forward to its promise of solving previously intractable computing problems, but have also begun to focus on addressing the inherent nuclear-level threat that such progress ironically represents to long-lived embedded devices and our mission-critical infrastructure.
Hi everyone, my name is Christine Kloostermans, and I'm a cryptography and security architect at NXP Semiconductors. My background is that I actually studied mathematics and then followed that up with a doctorate in side-channel attacks and post-quantum cryptography, which is a topic in this talk. At NXP, I work in long-term innovation, and specifically, I look at post-quantum crypto for embedded devices. I also, beyond PQC, like to look at various standardizations. I am involved in 62443, in an access control standard in CSA, and I also look at the mobile driver's license being standardized in ISO. Next up is Joost.
Thanks, Christine. I'm Joost Van Ness, a cryptographer in the PQC team at NXP. I have a PhD in cryptography on the topic of elliptic curve and isogeny-based cryptography, and I'm a developer of the proposal Psych to the NIST standardization effort. I've worked with and published on many of the post-quantum proposals, focusing on enabling PQC on resource-constrained systems in a secure fashion. It involves topics such as low latency, low memory, and side-channel secure implementations in software and hardware, but also, as you shall see today, integrations into protocols such as secure boot and secure update.
First, a quick intro to our companies. BlackBerry Certicom team are its specialists in applied cryptography. Founded in 1985, the same year elliptic curves were discovered as an alternative mechanism for implementing public key cryptography. Our founders recognized ECC's great potential. This was well before today's IoT era, back when wired telephones, fax machines, and snail mail were the primary tools for business-to-business communication. And one of our first ECC applications was securing fax machines. So we've been around long enough to have a perspective on the challenges of standardizing and adopting new crypto systems. This is one of our motivations for the webinar. In 2009, we were acquired by BlackBerry to help secure the BlackBerry ecosystem and its mobile phone production, establishing a way to govern and trust outsourced manufacturing. Today, we offer a number of products and services from crypto SDKs to PKI services, code signing, key management solutions, and systems for protecting keys and sensitive data and outsourced manufacturing environments. Our specialty is providing applied crypto solutions that are robust and easy to use, and our customers include industry leaders and innovators in a number of different markets. NXP, as I'm sure you all know, is a global leader in the embedded IC business with a broad portfolio of microprocessors across a range of markets, from automotive to mobile, smart home, smart city, communications infrastructure, and industrial. NXP combined the industry experience of two industry stalwarts, Philips Semiconductor and Freescale, a heritage which gives it unique industry depth and breadth. Like Certicom, NXP has a rich history in cryptography and has leveraged its prowess in smart card security, networking, and wireless technology to become a leading provider of secure ICs for its target markets. Today, we're going to see that expertise in practice on NXP's S32G vehicle network processors, which address the needs of next-generation vehicle architectures. Here showcasing the S32G's family's inherent ability to support crypto-agile design. And now, a brief introduction to quantum computing and what the cybersecurity industry is calling Y2Q. What is quantum computing? It's computing systems based on some fundamental principles or theories of quantum mechanics. Firstly, superposition, the idea that quantum systems can be in multiple simultaneous states. And secondly, entanglement. Quantum states can be correlated or entangled even though they are spatially separated, potentially separated by great distance. Quantum computing was first proposed by preeminent physicists in the 1970s. Ironically, they were thinking about the problems of simulating the interaction of a few dozen quantum particles. They realized, for instance, that a system of electrons with only 40 possible states would require 130 gigabytes of memory to store the state on a traditional computer. At the time, that just wasn't practical, even for a small quantum system simulation. The notion of using quantum computing principles to solve combinatorial problems started to gain interest, at least theoretical interest. But it took another 30 years to do something more practical, initially working on hybrid quantum computing platforms like those from D-Wave Systems, which were designed to solve difficult optimization problems through quantum annealing techniques. It took another decade to transition to more generalized logic gate-oriented computing that could potentially solve combinatorial problems faster than a modern supercomputer. Wow. And today, in 2022, we're on the cusp of that era called quantum supremacy, but not yet at a commercially viable scale. That's because while the theory is fantastic, large-scale implementation is far from easy. I first came across this chart from Google in 2018. Same year, BlackBerry Certicom team started looking at post-quantum cryptography. The notion of potential exponential growth in qubits really caught my attention. I've worked my entire career under Moore's Law and have a realistic perspective of its limitations. But the prospect of potential exponential growth in new computing technology was tantalizing. But it's 2022 now, and Google's prediction hasn't panned out. Possible does not mean probable, and you can't blame it all on COVID. I think the explanation is simple. This technology doesn't yet have its own Moore's Law. And I believe Moore's Law is fundamentally a law of economics and return on investment. But money is being spent, and progress is being made. Let's take a look. I've spent time trying to get a handle on where the industry is today, and this is what I've come up with. Interesting to note how core technologies from these industry leaders use different physical phenomena, and yet they're more or less all about the same stage. Far from the 1,000 qubits Google had predicted, and no one has yet cracked much more than 100 logical qubits. But companies like IBM with the most experience seem the most confident in terms of their roadmap. Also, the unit of measure is no longer absolute number of qubits, but looking more at logical qubits and quantum volume, a measure of qubit or circuit quality. And another critical factor, as with any computer, is clock speed, or in IBM parlance, circuit layer operations per second, which together make a proxy for quantum computer performance. So despite the relatively slow pace in a Moore's law sense, significant progress is being made. And another observation, the programming tools, even the cloud platforms, are already developed to abstract away the hardware and take things like circuit construction and noise maps into account in performing calculations to optimize performance on a given platform. There are a lot of reasons to be optimistic. Now that I've convinced you of the feasibility of quantum computing, it's time to talk about the dark side, Y2Q, the year quantum computers will scale sufficiently to crack traditional crypto systems. Not long after, they may be for rent on the dark web. Y2Q got its name from the Y2K problem. But Y2K was something much more trivial, and fixing it cost U.S. industry over $100 billion. Y2K was so expensive due to the massive amount of legacy software to upgrade and test, and a last-minute rush by stragglers to fix issues. Hopefully, we've learned some lessons. So Y2Q is the motivation for post-quantum crypto algorithm development. Again, that's because the same quantum computer that can be used to design a complex chemical process can also be used to break traditional crypto systems. We've seen this work. For instance, Shor's algorithm for integer factorization was demonstrated using quantum computing techniques way back in 2001. Baldesky Research wrote a detailed paper to parameterize the computation ability of a quantum computer needed to crack ECDSA. They say a sufficiently capable machine, one I imagine might be available in 5 to 10 years, could crack 384-bit ECDSA in 24 hours. The takeaway here, cracking algorithms work, and quantum computers may be here sooner than you expect. That should have you thinking about lessons of Y2K and the Y2Q imperative to design for crypto agility. If you spend some time around different industries, you'll come to realize that many operate at their own pace due to different product life cycles. As a result, Y2Q risks weigh more heavily on some industries than others. The consumer electronics industry is one of the more fast-paced, with ever-increasing demand for new products and new features which drive the chip industry. The mobile phone developers have some time. While the automotive market's picked up its own R&D pace, it still takes 2 or 3 years to bring a new vehicle to market. If you add the availability of new chips, you tack on another 18 to 24 months of R&D time. And if you're building airplanes or satellites or anything with a much longer product life cycle, you may already be well behind. But if you're not looking at this problem yet, Osgood's inequality theorem suggests you need to start. An abrupt breakthrough in quantum computing may really put your designs at risk. Companies failing to mitigate that risk may ultimately pay a high price. Fortunately, as you'll hear next, Crypto-Agile design options are available now.
So, now that Jim has told you all about Y2Q and why this is a problem, I will continue to talk about things we can do to mitigate Y2Q and resolve this problem. The first direction I want to talk about is post-quantum digital signatures. At a high level, these work just like classical RSA or ECDSA-based signatures. An image hash is signed with a signature, which can be verified by the receiver to be a valid signature over the image they receive. This gives authenticity to the image. Hash-based digital signatures are one type of these post-quantum signature schemes. These particularly have a few advantages. For one, they're based on the well-founded cryptographic primitive of hash functions. Hash functions are used in many applications now already, and their security is well understood and well studied, and therefore this primitive is quite reliable. From an embedded perspective, this also means that acceleration of this primitive is already available on embedded devices now. The existing acceleration or hash primitives can be reused for these hash-based digital signatures. This makes them a particularly attractive choice for constrained devices. Another advantage is that they're standardized already. So in 2019, RFC 8554 was presented. This includes latent Micali digital signatures, which are a type of hash-based digital signatures. A year before that even, RFC 8391 presented the extended Merkle signature scheme. This is another type of hash-based signature, but also already standardized and quite reliable. Last year, this was put forward extra by the US NIST. So NIST is the National Institute for Standardization and Technology, and they advise these type of hash-based schemes for applications like code signing. In a special publication, they standardize specific parameter sets for these schemes that they endorse using for applications that allow hash-based digital signature schemes. They offer many parameter sets, but at least some can offer a quantum resistance up to 128-bit quantum level, which corresponds to 256 bits of classical security. What should be taken into account is that hash-based signatures do need to manage a state. Their construction consists of combining many one-time hash-based signature schemes. As this name applies, each of them should only be used once. Maintaining this state can lead to problems in high-performance applications or in glitch-sensitive applications. Additionally, in the worst case, the one-time signatures can be depleted. This means that in absolute disaster scenarios, they might not be worth the risk if a backup system cannot be put into place. Because these hash-based digital signatures of the previous slide are not for all applications, more tools are needed to prevent Y2Q. To that end, in 2016, NIST set out a call for proposals to gather a list of potential algorithms to additionally be standardized. At the time, the idea was to publish these this year already, but due to delays, this will likely be 2024 in the end. The call for proposals was for both digital signature schemes and key exchange or key encapsulation mechanisms. These latter have the goal of communication encryption. Of all the submitted proposals, none offer both the key size, ciphertext size, and efficiency of ECC. Some offer speed at the trade of very large keys, some offer small keys but are very slow, and some are somewhere in the middle. Therefore, there isn't really one best algorithm. This will very much depend on the application and its constraints. The NIST selection of algorithms by now went through several rounds, after which we are left with 7 finalists and 8 alternates. The finalists are those of which a few will likely be chosen by NIST to standardize over the next 2 years. The key encapsulation mechanisms focused at encryption are called Crystal Kyber, Entrue, Saber, and Classical McLeese. The schemes for digital signatures that made it to the final 7 are Crystal's Dilithium, Falcon, and Rainbow. The 8 alternates I mentioned serve as a backup. These either need some more study because they're based on rather new primitives, or are based on more conservative security assumptions, which makes them rather slow, or might serve to work well only in very specific use cases. A subset of them might still be standardized, but maybe not in the first round of standardization. An exception might be the Sphinx Plus scheme, which was classified as an alternate, but showed reliability and promise. The focus of this presentation is the scheme Crystal's Dilithium. We chose this scheme because it's very suitable for embedded applications, as we'll see in the next slide. So, the Dilithium digital signature scheme. This scheme is based on what are called ideal lattice problems. Like the hardness of, for instance, RSA is based on the hard mathematical problem of prime factorization, lattice problems are a class of mathematical problems that are considered hard for even an adversary with a quantum computer. Crystal's Dilithium is based on a specific type of lattice called an ideal lattice. This means that there is an additional underlying structure to the lattice, and this enables faster computation and thus better performance of the scheme. Dilithium, compared to some of the alternatives, has a design strategy that works particularly well for embedded devices. For instance, it does not have any Gaussian sampling, which can be hard to do efficiently and securely on an embedded device. It also does not use any floating point operations. These on a small device would often give trouble. Additionally, this scheme can also benefit from current hardware design, since it can already benefit from things like SHA-3 acceleration. Then next, a large advantage are the key sizes. They are larger than classical algorithms, but they are reasonable. If we look at the key size on the right, they look large with a couple of kilobytes, but not ridiculously large. Compared to the RSA public key, Dilithium is about 5 times bigger, with a 20 times factor for ECDSA. Also in signature size, these Dilithium signatures are about 10 times larger than RSA and 40 times larger than ECDSA, which is, I mean, a significant overhead, but really not ridiculously large that it won't fit on an embedded device. This is of course good because real constrained devices often have limited memory and have a real challenge to deal with the sizes that go around in PQC algorithms. Additionally, the scheme is rather fast in verification. This of course depends on the exact implementation, the platform, and what kind of hardware acceleration is on there, but it can be at least as fast as ECC. Signing is slower than RSA and ECC, but feasible enough, especially compared to the hash-based alternatives. Lattice-based algorithms like Dilithium perform better on embedded devices. Well, by now, as an introduction, we've talked about Y2Q and why it is a problem, and we've talked about post-quantum digital signature schemes and how they can help to mitigate Y2Q. Now it's time to look more at the practical side. And to do this, we look at a specific use case, namely the use case of Crypto-Agile quantum-safe secure boot, of which we will give the details in the following parts. Before diving into secure boot and the crypto agility, we first look at the specific domain and platform we will be looking at. The domain is that of automotive, aka the embedded devices in cars. Specifically, one of the devices that is managing many car functionalities is the NXP Gold Box. This is a service-oriented gateway that enables a few vital car functionalities. For instance, it enables secure networking across vehicle domains. This means, for instance, as well, making sure that the communications between the powertrain and the autonomous driving modules occur securely. It also takes care of secure cloud connectivity. This way, the vehicle can send and receive new data from the cloud. This functionality also enables upgradable software-defined vehicles that can be updated over the air. This Gold Box is powered by the NXP S32G2 vehicle network processor. This will also be the platform we will use in the coming demo. This chip enables new intelligent vehicle solutions that bring cars to the future. For the purpose of looking at quantum-safe solutions, automotive is a particularly interesting use case. For automotive applications, Moscas theorem, which Jim mentioned in the introduction, kicks in. Cars that are under development now may be in the field for a long time and outlive a potential Y2Q. This makes our demo very relevant. One of the main security functionalities the S32G2 offers is that of secure boot, making sure at every boot of a chip that it's initializing securely and running the boot code and firmware that is expected is integral to ensure that malicious code cannot simply be loaded into a car. I will now give the word to Joost, who will explain how the secure boot flow works in the S32G2.
Thank you, Christine. Let's have a look at the high-level boot process on the S32G2. The boot flow is designed as a sequence of chained bootloaders, each verifying a respective signature before passing on control. This enables lots of customization to be able to handle a wide variety of applications. In the secure startup process, the S32G2 starts by executing a trusted read-only memory firmware called the boot ROM. It is responsible for verifying, decrypting, and loading the security firmware for the hardware security engine, also abbreviated HSE. The HSE then takes care of kicking off the next boot stage by verifying and possibly decrypting the application bootloader, and by releasing the application course from reset. The application bootloader is fully customizable. For example, it can start an operating system or it can extend the boot chain even further. In this demo, we target the second stage bootloader, in which the application bootloader is verified and executed by the hardware security engine. Before secure boot can be used in the field, an installation process is required. We load an application bootloader together with an initial proof of authenticity into the HSE. The proof of authenticity is a pre-quantum digital signature over the bootloader with respect to a previously installed trusted public key, for example, RSA or ECDSA. If the signature verifies, the HSE will install the bootloader and calculate an internal reference proof of authenticity, which even today is secure in the presence of quantum adversaries. Once the system is in the field, the HSE firmware will verify the reference proof of authenticity on the bootloader and continue only if it is successfully authenticated. Note that since this reference proof of authenticity is quantum safe, the boot flow remains quantum safe as long as the initial proof of authenticity was verified before quantum computers are far enough advanced. The initial proof of authenticity requires a trusted public key and, as a result, a secure key management of the private keys and signature creation. This is where the BlackBerry Certicom signing appliance plays an important role. I will hand back over to Jim to give you insight into BlackBerry Certicom's signing appliance.
For robust security, it's critically important to protect secret keys and sensitive data, but that doesn't need to be difficult. And depending on what you're using your keys for instance, for production or R&D, you probably want different options. BlackBerry gives you the best of both worlds, robust key management and options for ease of use, with support for traditional public key crypto and quantum-resistant signature algorithms, support for local M-of-N smart card-based access to keys, and support for remote network access via GUI or REST API. BlackBerry Certicom makes post-quantum crypto key management operations easy and secure. As you'll see from the demo, the appliance form factor with built-in HSM is especially convenient. To start the demo, I'd like to walk you through some of the features of the BlackBerry Certicom code signing server and show you how it's both production ready and user-friendly for R&D teams working on post-quantum or traditional crypto applications that involve code signing and key management. So as an administrator, you're typically doing things like managing users. And here you see I have a number of users. I could add additional users. And we've added a user already for the NXP demo. The NXP user has just a limited number of permissions to access the UI or the REST APIs. They're a member of one key group. Administrators also manage tokens. Tokens can be smart card set, M of N, or they can be YubiKey tokens for remote access control. Again, M of N down to 1 of 1 for YubiKey access to a particular key group. I keep mentioning key groups. Let's take a quick look. I can have multiple key groups. I can create new key groups. Within a key group, there are a number of keys that I can add. They share a common protection scheme, say module protection, password protection, token protection. Module protection is just basic protection by the HSM itself, so they can only be accessed within the HSM. Password protection requires a password in addition to that to access or use a key. And then token protection requires, again, a YubiKey or a smart card set to be presented to get access and use a key. So a lot of different features. Of course, there's also audit logging and export. There are settings for the server itself. And then, of course, if an admin has certain rights, they can sign and encrypt things themselves. Now let's log out and show you what a user can do with the system. And so we're going to log in and see NXP user and take a quick look around and then do a signing operation. So the NXP user is coming up, sees all the key operations that are things that have been signed, but now they have a look at their key group and say, okay, I'm a member of this key group. What can I do with this key group? So they can look and say, well, there's some other users in the key group. I know who those people are. That's great. The NXP user doesn't have any admin in this key group, but they can create new keys and they can use keys. Let's say they want to use this Dilithium 2 key, which is what we'll use in the demo. How would you use this key? Well, let's start by downloading it. We want to download the public key. And now that we've got the public key downloaded, we also want to do some signing operations. So I want to sign something. I get to choose a key from my key group. I'm going to choose this Dilithium key. Now I want to sign a file. I get to upload that file, select it. I'm going to select this binary image for the S32G2. And okay, and now I'm going to sign it. I submit a signing request through the GUI. I refresh the screen. Look, signature is available. Awesome. Okay, download that signature. There it is. Okay, now I've got a signature and a public key I can use to verify that, and I can manually do something with that on my target port. But what if I want to automate that? Well, that's where the REST API comes in. As I mentioned, it's very developer friendly, so a developer can tie this into their development tools. Every time they do a build, they need a non-production key for code signing. They can use the REST API to submit a file, a request with the hash of the file itself, and get that code signed and again carry about their process in automated fashion. So that's how NXP is going to do it. I'll hand it over to them and they'll walk you through the demo on a real target hardware showing the Dilithium 2 signature process and verification through, again, through the REST API with the signing server.
As mentioned earlier, the demo targets the second boot stage, where the custom application bootloader is verified with a digital signature by the hardware security engine. We integrate the Dilithium signature scheme into the HSE firmware and replace the pre-quantum signature schemes such as RSA and ECDSA with Dilithium in the boot process. A Dilithium signature can be installed before deployment of a device or updated in the future in the field by a super user. The key pair is generated with the BlackBerry Certicom signing appliance through a REST API, and the public key is imported into the HSE. The signature over the bootloader is acquired using the same REST API. We will now demonstrate how one can install a Dilithium verified boot image onto the device.
So here we have the code that installs the customer bootloader onto the S32G2. We see that deep in the code, a Dilithium key is imported from Flash into the HSE key catalog. Some options can be defined for the Dilithium signature. This can be, for instance, which parameter sets and hash functions are used. This key is then subsequently used in the HSE boot as a proof of authenticity to verify a Dilithium signature over the bootloader. Note that these two steps could be separate processes. This way, multiple images can be verified against the same Dilithium public key as well. We can now compile this code to create a binary that can be used on the S32G2. We now want to generate the Dilithium signature over the generated code. To do this, we use the BlackBerry Certicom signing service, which signs the binary with the key generated in the key generation step. We see that the binary is first hashed. The signature is then computed over the 256-bit hash output. As a result, we now have a binary that installs the customer bootloader with the corresponding authentication in the form of a Dilithium signature. The next step is to load the binary blob containing the image and signature onto the S32G2 board. We do this using trace32, which flashes the binary blob onto the board. At the end of this step, the installer is successfully flashed and on reset will be executed by an application core. On first boot, the installer securely installs the customer bootloader. To that end, the proof of authentication, namely the Dilithium signature, is verified by the HSE. If verification is successful, the bootloader is installed. A reference proof of authenticity is computed for faster subsequent boots. We see that this complete process only takes 14.2 milliseconds. We can now securely boot the customer bootloader.
Here is a brief overview of the performance impact of switching from RSA or ECDSA to Dilithium. We emphasize that this is only a demonstrator and that performance can still be significantly improved, in particular by integrating SHA-3 hardware acceleration. Notably, the public key and signature sizes increase significantly. However, since the S32G2 is a powerful device with sufficient memory to work with, this can easily be handled. We also see an increase in the runtime, though even for the largest parameter set, we remain below 30 milliseconds. Due to the clever design of the S32G2 boot flow, the Dilithium signature is only verified at installation time, but not at boot time. As a result, although there is indeed a minor impact on the installation time, the boot time is almost unaffected. We believe a transition to post-quantum secure boot can be considered practical for this platform.
So start now or deal with much more expensive headaches later. Y2K was a $100 billion problem that took years to address, and it was on the calendar. Likewise, transitioning crypto algorithms is not something the industry can do overnight. Simply switching from DES to AES and SHA-1 to SHA-2 took 15 years of misguidance and industry effort. For Y2Q, we don't have a date on the calendar to focus our attention, and that seems to be the problem. Because if you're waiting for the date, you'll surely be too late. To start working through these problems now, please give us a call.
Hi all, thank you for joining our webinar. I'm Chris from BlackBerry Marketing. We can now host some Q&A. I'll run through a little bit of just housekeeping first. The slides the presenters went through are available to download. In the screen where you see the webinar, hopefully on the right-hand side, you should see a window called Resource List, and there are the slides to download there, as well as links to both BlackBerry and Certicom papers and websites. If you have any questions you'd like to ask our presenters, please use the Q&A box, again, on the webinar screen below the window where you're seeing the slides. We'll then see those questions come through. So we have a couple of questions that have come through already. So I think for the first one, When do we expect NIST to announce? I'll ask Christine to answer that if possible.
Yeah, sure. Thanks, Chris. So this question has a bit of a disappointing answer, I guess. NIST would have been expected to announce the winners or the to-be standardized algorithms at the end of last year. Unfortunately, delays we are guessing writing the document and legal approval has pushed it out up until now. We still hope to hear the final announcement before fall, but really to get a definitive answer, you would have to ask NIST.
Cool. Thank you very much. So there's one message just mentioning that the NXP post-quantum cryptography link is broken. It was working for me yesterday. If it is broken, we'll send a follow-up email after the event, just including the links. We'll check them all before they go out. So I'm not sure if that's an issue with someone's system or who they're connecting through, but my understanding is it was working, but we'll send it as a follow-up to this also. So a question that has come in. It sounds like the measurement for qubits changed, but is there any explanation why Google went from 72 qubits in 2018 to 53 qubits in 2021? Jim, are you able to answer that one?
Not in great detail. I think the main that Google was out in front with, say, noisy qubits and kind of came back to the drawing board with better circuitry and focused really on more the quality of the systems, et cetera. So I think that they just pulled back a little bit in terms of overall what they're reporting. And again, that's aligned with, again, I typically rely on the IBM website to explain what they're looking for effective quantum computing system, which is a lot of different things. Again, the quality of the qubit circuits themselves, how they're architected to the different layers, and then, of course, also the clock speed, so that general idea of coming up with a different kind of measurement. So to that question, I don't know exactly why the absolute numbers changed for Google, but generally speaking, lower number of qubits, and I think they're quality qubits probably rather than the absolute physical qubits that they're talking about now. And again, better measurements of true quality circuitry that you can compare apples to apples on. And again, part of that, if you can appreciate it, so that these circuits, they also have a map of that circuit that they feed into the computer program, the operating system, if you will, that runs it, so that they know how to optimize for a given circuit, how to optimize the code that runs it to get a result. So in terms of that, the sheer number of qubits isn't that important, although you need more and more qubits to do more intra calculations. But why the Google number dropped from what they're reporting, I can't say exactly why that is.
Okay, cool. Question for Juice, I think. Is AES 256 based symmetric crypto considered to be post-quantum capable? Juice, you may be on mute.
Oh, sorry?
You were on mute, you are not now. So you can...
Okay, thank you. Yeah, sorry. So yeah, typically AES 256 is considered PQ capable. The very rough estimate for post-quantum versus classical for symmetric schemes is that you have to kind of double the key size compared to what you were used to. So if you consider AES 128 okay today, then AES 256 would be okay against a quantum adversary. This puts some details under the carpet, but I think as a rough estimate, it holds up quite well.
Okay, cool. So someone's asked again about slides. So there's a PDF version of the slides that you should be able to download from the webinar main page. The recording of the webinar will be available from the same link that you came to watch it live. So that link should be available for the next 2 or 3 days or so. And then hopefully within 3 days, we'll have the webinar loaded to the BlackBerry QNX YouTube page also. Cool. So another question come in. I have a more high-level question. I would imagine that there are some embedded devices connected to the internet and some not. If this is actually accurate, how much would this affect the attack risk and consequently the cryptography schemes used to ensure security? Used in order to ensure security. Christine, is that one you can pick up?
Sure. Thanks. A good question. Yeah. So if you look at post-quantum or quantum safe schemes at a very mathematical level, usually you look at something like ECC and RSA and just judge that it's faulty or not secure against quantum adversary anymore. Of course, in practice, you are right, and there are embedded devices that are connected to something, or those that are connected to nothing, and those are connected to the internet, and those where an adversary has access to certain cryptographic material, and those where this is not the case. It will depend very much on the use case where the priority lies on how fast to update. But in the end, if you want to be really quantum safe, it is desirable to update anyway. It's just that you are right that the risk might differ, and therefore the priority in updating might differ. I think Jim also wants to, yeah.
Yeah. So just to chime in, I'll say, so Stuxnet and the attack on the Iran nuclear program, that wasn't a system connected to the internet either. So don't get too comfortable with, oh, I'm not connected to the internet. You know, if you have any exposure for software updates, you have exposure.
And just on that, I think something you mentioned before, what would you say are the systems or the vulnerability points that are most at risk from Y2Q? What are the things that are the most urgent to start working on?
Yeah, I think I'd say it's critical infrastructure, things that are going to be around for a while that we rely on in our daily lives, and again, that could be vulnerable to a point of attack. The example, I talked to someone last week and said that in 2004, the East Coast grid went down due to a power outage, but that East Coast grid went down for about a week, and that was just at the limit of how long society can tolerate the grid being out, is about a week, and then it gets kind of ugly. Then it gets into last man on earth kind of scenarios where you don't want to be there. So I'd say anything like that where you can have widespread disruption is going to be a concern, critical infrastructure, transportation infrastructure, et cetera. And of course, again, if we're talking about in warfare equipment, anything that's basically driving national security would be a big concern, which is why, again, NIST and the NSA are among the entities really pushing for the migration to this quantum resistant scheme.
Okay, cool. So another question. So you mentioned, or I think during the presentation, Christine mentioned, the keys are slightly larger and the signing is slightly slower than RSA. Although that may not be material in most cases, are there any use cases where that is a material issue? Juice, do you want to answer that one?
Yeah. Again, it would depend very much on the context. So especially for signing software, often the signing speed is not too critical, right? You have a big, powerful server that has to put out some packages. It's really the latency on the small IoT systems that is often your bottleneck, and is really where the post-quantum sizes and then the increase in latency starts to matter. But there are also use cases where you need signing of messages on your systems, on your small systems. I don't know if you want to do some payment on your device, if you want to do some kind of payment terminal application, if you want to run that, you might have to sign some messages. I think in those use cases where you have to do signature generation on a small system, the impact is going to be a little bit more felt than if you only have to verify in case of secure update or secure boot. Right, so those are a bit more challenging use cases.
Cool, thank you. So that's all the questions we've had in, unless any come in the next 30 seconds or so. I'd just like to say thank you for everyone for joining. Thank you, our presenters, for both presenting and answering questions. Again, the presentation will be available on the same link to view on demand for the next 2 to 3 days. We think we've figured out the link issue for the paper. I will fix that in the next hour. So if you come back to the on-demand video, that link should be working in about an hour's time or so once it's replicated across various servers. And if you have any other questions, by all means, link up with any of our presenters. Their details are on the webinar screen. You can find them via LinkedIn and add them and message them. They've all agreed, or at least not objected to that happening. Thank you very much. If there's anything you do want to pick up on, like I say, talk to one of the presenters directly, and we're always happy to have a follow-up conversation offline. Is there anything anyone else wants to add?
Yeah, so one quick comment. So I did have at least one person contact me and say they couldn't hear the demos. So we'll make sure that the recording of this, make sure that there's no audio problem. I don't know if it's a browser issue or something, or an encoder.
Yeah, so some of it, so on my test attendee view, it definitely played fine. So I don't think it's an issue for everybody, but we'll definitely double check and test the on-demand version to make sure it's all working correctly. But like I said, if you did have any audio or visual issues, if you give it an hour for the system to reboot to video on demand, you should be able to go back and just check the bits that you may have had a problem. Cool. If that is all and there's no other questions, thank you very much, everybody. Hopefully we've all learned something and we'll be a bit more secure going forward. Thank you.